Frequency matters. Optimizing Fourier features for neural field. Today I'll present our work on improving nerve rendering quality through optimized learnable Fourier encoding. Standard nerve struggles with high frequency detail, producing blurry results. This is due to spectral bias. Neural networks naturally favor learning low frequency patterns over fine details. Our work addresses this by replacing fixed position encoding with learnable Fourier features. This enables sharper rendering essential for digital content creation. Our goal is to validate nerve baseline and investigate how learnable encoding improves high frequency detail preservation. First, we reproduce the canonical nerve baseline in PyTorch. This ensures our implementation matches published results both qualitatively and quantitatively. For evaluation, we use the LLF dataset, especially the flower scene, a forward facing real world scene with complex lighting and detailed texture. Our baseline uses 8-layer MLP with positional encoding. The neural network processes 5D input, combining 3D position coordinates with 2D viewing direction through sinusoidal embedding. This allows the network to learn view dependent effects like specular highlights. The network has 256 hidden units with a skip connection at layer 4 that helps preserve fine detail by allowing direct information flow from the input to deeper layer. The baseline uses a two-stage hierarchical sampling approach. First, a coarse network uniformly samples 64 points along each camera array based on the density estimate from this coarse pass. The fine network then important samples the additional 64 points, focusing computation on regions with high density. Finally, the baseline integrates RGB values and density along camera array using volume rendering. Our model also uses the same 8-layer MLP with a key enhancement. We replace a fixed position encoding with learnable sinusoidal embedding. This allows the network to adaptively learn the optimal frequency representation for each scene. We also doubled the network hidden units to 512 and also the batch size for stable gradient. The hierarchical sampling and volume rendering is pretty much same, but the key difference is learnable encoding, wider network, and larger batch size. Learnable Fourier encoding was done by replacing the fixed position encoding with trainable Fourier features. The mathematical formulation is gamma of p is equal to the concatenation of sine and cosine term of each Fourier frequency fi. Unlike fixed encoding, the frequency where the frequencies are predetermined, here each frequency is learnable and stored in log space. The log space storage is crucial and allows proportional gradient updates for all frequency band, regardless of their magnitude. For evaluation, we use the flower scene from the LLF dataset. And for the evaluation metrics, we used three metrics, which is PSNR, SSIM, and LPIPS. For training, we trained both the baseline and the new model for 200 and 1000 iteration with Adam optimizer with a learning rate of 5 into 10 raised to minus 4. The batch size of the baseline was 1024 and for the new model was 2048. The frequency band for position was 10 and the frequency band for view direction was 4. This was same for both the baseline and the new model. Both were trained in RTX 3090, which had a VRAM of 24 GB. These are the results for the baseline and the new model. As you can see, the PSNR had a huge jump of 6 decibel for the learnable positional model. The SSIM and the LPIPS also slightly improved compared to the baseline. These are the WNP runs results. As you can see, the baseline plateaued at 30.6 decibel for the PSNR, whereas the new model plateaued at 36.6 decibel for PSNR. This is the qualitative results for the new model and the baseline. As you can see, the new model is more crisp than the baseline. As a conclusion, we can say that learnable position encoding is a major innovation. Wider network combined with learnable position encoding and optimized training helped us to achieve a 6 decibel jump in PSNR compared to the baseline.